So good morning everyone. Today we are going to start unit number 5 and that deals with support vector machines and neural network. So this unit actually is being divided into two parts. In section 1 we are going to deal with support vector machines and in section 2 we are going to deal with artificial neural network. So to begin with, we are going to discuss now section 1 of this unit and that is support vector machines. So what we are going to discuss in this unit, I'll be introducing what is support vector machine. It is abbreviated as SVM. We'll talk about linear SVM, optimal margin classifier, then we'll go for soft margin classifier, or we'll see the concept of maximum margin with noise. Then we'll see non-linear SVM. We'll be focusing upon few kernel functions, those can be used. And finally, we'll look at how support vector machines can be used for multi-class classification. So this is the agenda for this section of unit number 5. So let's begin with what is SVM. So before actually going for SVM, let us revise few concepts. SVM is a supervised machine learning algorithm. SVM is a supervised machine learning algorithm. And this machine learning algorithm can be used as classification or regression. So for both the tasks, SVM can be used. But the most popular use of support vector machines is for classification. So we know what is supervised machine learning. So in fact, we have gone through 3 kinds of machine learning algorithms: supervised machine learning, unsupervised machine learning, and reinforcement machine learning algorithms. We have discussed few algorithms under this category of supervised machine learning algorithms. We have not yet gone through unsupervised algorithms, right? But we have gone through supervised machine learning algorithms. So under supervised machine learning, this is a general process. Please look at this block diagram. So what we have is, we are having the training data. So in training data set, we are having various examples provided in the form like x comma y, where this x is my feature vector and y is the associated. So I am having input values. So for every sample, we are having x value, that is the feature vector, and also we know the output, that is the class of that sample, right? So we are having such kind of training data with us. Then we are making use of some learning algorithm which will learn from this training data set. After learning, this learning algorithm will prepare a model, right? Or this learning algorithm will give us some hypothesis, and based on that model, it is possible for us to test the unseen data. So once this model is being created, what we do is we provide the test sample or the new input x to this particular model, and based on whatever is the experience, based on whatever is the knowledge that has been learned by learning algorithm, this model will predict the class for unseen data. So this is how our supervised machine learning algorithm works. Now where is the place for this support vector machine? As I stated, a supervised SVM is a supervised machine learning algorithm. So obviously, our support vector machine can be placed at this learning algorithm place. So we are having some training data. That training data is being provided to SVM. The model is being created, and then the classification for test samples can be done. So this is where our support vector machine, or this is how our support vector machine works as a supervised machine learning algorithm. Now let us see one example. In fact, we have gone through such kinds of examples many times, but once again, for the completion of our discussion, we are having this example. So let us assume that we are having some training data with us, and this training data is being described. Every training data is being described with two features, X1 and X2. Right? So every sample is being described with these two features. Let us assume that we are having training data set with two classes. So we are having circle class and we are having triangle class. So we are having few samples or few observations from circle class. Look at this. These are the samples. Those belong to my circle class, and also we are having few samples from the triangle class. So these are the samples, those we may have from this triangle class. Now, what our supervised learning algorithm will do, and what is actually the goal of our supervised machine learning algorithm? We want to classify these observations into two classes. We want to distinguish between these examples, right, based on the features of these examples. So by applying machine learning algorithm, what we do is we come up with a hypothesis, right? As this data is two-dimensional data, the hypothesis looks like a line. So this line is segregating the data into different classes. So meaning towards this side we are having circle class, and towards this side of the line or hypothesis we are having the triangle class. Okay, so such kind of hypothesis, we may have many such kinds of hypotheses. We have seen these concepts earlier, if you remember. So we are having the hypothesis space, and in that hypothesis space we are having various such kinds of hypotheses. In this particular example, we may come up with many different kinds of lines. Those are the hypotheses, right? And our supervised machine learning algorithm, what it will do is it will pick the hypothesis or the optimal hypothesis based on some criteria, right? So let us assume that this is the hypothesis that is being picked up, and this hypothesis is actually known as the decision boundary. So why this name decision boundary? Because by making use of this hypothesis, it is possible for us to decide the class of the sample. So towards one side of the hypothesis, we are having one class, that is circle. Towards other side of the hypothesis, we are having another class, that is triangle. So if I am having, say for example, any unknown sample, suppose I am having here some test sample. I don't know the class of this sample. Right? Now, once I am having my hypothesis, if I am having such kind of a test sample provided for classification, what my system or what my model will do? My system will check for this sample, and if this sample is now, this is my decision boundary, right? So if the sample belongs to this side of the boundary, then this sample, this black test sample will be classified as class circle. If my test sample is towards this side, then definitely it will be classified as the triangle, right? So decision boundary actually decides the class of the sample, right? So this is how actually our classification algorithms work, supervised classification algorithms work. And this is a simple example having feature vector with two features. So every sample is described with two features, right? SVM actually uses a technique that is called as the kernel trick. I'll repeat, SVM uses a technique called as kernel trick to perform some complex data transformations to find an optimal decision boundary that will segregate my classes, right? So ultimately, the goal of any such kind of supervised machine learning algorithm is to come up with a decision boundary. We are having various different kinds of algorithms, and every algorithm works with some principle so that that algorithm will provide us the optimal boundary, right? Similarly, our support vector machine is a technique that is using kernel tricks to perform some complex data transformations. And after performing these data transformations, our SVM will help us to find the optimal decision boundary that will classify my samples, right? So in this unit, we are going to discuss the details of support vector machines, the concept, how support vector machines can be used for linear as well as non-linear data classification, how support vector machine can be used for multi-class classification, and the mathematics behind, right? So let's begin with the kind of data that we may have, right? So let me proceed now with the kind of data that we may have. So we are having linearly separable data and we are having linearly non-separable data. In fact, we had a discussion before regarding these kinds of data. So once again, I'll be focusing upon linearly separable data and linearly non-separable data. So let us look at this figure. So once again, what we have is, we are having the training data that belongs to two classes, circle and triangle, and every sample is being described with two features, x1 and x2. And if we want to classify this data, we may come up with a decision boundary like this, which is a linear function, right? So a decision boundary that separates the samples belonging to two different classes. And as I stated, if I am having such kind of a distribution of data, I may come up with a linear function that actually distinguishes the data from two different classes, right? Now, a data set is linear if the data belonging to different classes. I'll repeat, a data set is said to be linearly separable if it is possible to draw a line that separates the data points belonging to different classes. Right? So, in linearly separable data, it is possible for us to find out a linear function or a linear decision boundary. Right? But if we look at this another sample or another example, see here how our data points are distributed in this two-dimensional space. Once again, every sample is being described with two features x1 and x2. But see how these samples are spread in this space. Now, if I want to classify these samples into two classes, say circle and triangle, it may not be possible for me to come up with a linear function or a line. Do you agree with me? Yes? Do you agree with me?
Yes, ma'am.
So if I want to classify these samples into two different classes, then as the distribution of data is as shown here on this figure, it is not possible for me to come up with a linear function, right, that segregates my data. So I need to think of some function that is non-linear, right? So I may come up with such kind of a non-linear function. Here we are using a circle, right? So here we are using this non-linear function as the decision boundary. Okay, so a data set is said to be non-linearly separable if data points from different class cannot be separated by a linear function. So if it is not possible for us to come up with a linear function to separate out data belonging to different classes, then we should come up with a non-linear function. And a data set is said to be non-linearly separable if data points from different class cannot be separated by a linear function. Right? And in such situations, we need to make use of a non-linear function or a non-linear decision boundary. Right? So please remember, we are having two kinds of data. Linearly separable data we may have and linearly non-separable data we may have. Now, why we are discussing this? Because whenever we talk about vector machines, SVM provides solution to classify both kinds of data. I'll repeat, support vector machine provides solution to classify both kinds of data. So it is possible for us to come up with a linear function or a non-linear function depending on the nature of the data, right? And SVM allows us to pick such kind of a function, maybe a linear or non-linear. So SVM provides solution to classify such kinds of data, linearly separable data as well as linearly non-separable data. Right? Am I clear? Yes? Fine. So now let us proceed with one example. I am going to explain now how this concept of SVM is evolved, right? And for that reason, I am having here one example. Suppose we are having some training data. For simplicity, we are having here only a one-dimensional data. What does this mean, 1D data? Every sample or every example with only one feature. Right? So see here, we are having many different samples. right? So these circles are various observations. And as I stated, we are talking about one-dimensional data, right? And this problem, let us assume that this problem is having the medical domain. So we are trying to find out whether the sample is malignant or not, whether the sample is cancerous or not. And every sample, we are assuming here that every sample is described with a single feature, and that feature is tumor size, right? So whatever we are looking at here are different examples, different samples in our training data set, and every sample is being described by making use of a tumor size. Okay, so as we move on from left hand side to right hand side, the tumor size goes on increasing. So these samples towards left are having tumor size which is small, and these samples which are towards right, those are having the large size of the tumor. I hope you must have understood what is our data. Okay, now this data belong to two different classes. Okay, actually these samples are showing the tumor size as I stated, and we say now that these samples belong to two different classes. So what are those two different classes? See, we are having here few samples. Those are depicted here with green color, right? So these samples are the samples which are not having malignancy. So green samples are the normal samples or not malignant samples. So green samples are not having cancer, right? So these green dots show the samples, those are not malignant. Whereas these red dots are the samples, those are having malignancy. So these red samples are malignant samples and these green samples are non-malignant samples, right? So we are having the samples from two different classes. Okay, now if you look at these samples, what we observe is, see here, the non-malignant samples are having tumor size comparatively small than the malignant samples. So malignant is comparatively large than the non-malignant samples. Okay, now what next we are going to do? Suppose we want to classify these samples into these two classes, malignant and non-malignant. Obviously, what we need to do is we need to come up with some threshold, some decision boundary. So whatever purple block you are observing here, this is my decision boundary. Okay, or this is a threshold. Why I am saying this is a threshold? Because right now we are talking about one-dimensional data. So simply this decision boundary is nothing but a threshold. So how we are going to define this threshold? We are making use of some criteria and we are coming up with this threshold. And let us assume now that we have picked up this threshold. So how we are making use of this threshold now? If the sample is towards left hand side of the threshold, this will be classified as non-malignant, green. And if the sample is towards right hand side of this threshold or the decision boundary, it will be classified as malignant, red. Right? So this is the simple criteria that we are making use of. Okay, now let us assume that we are having this new sample. So this red dot is my new sample, test sample, and I want to categorize, I want to classify this sample. So what my system will do in this scenario? Anybody? What we want, this is our test sample. New sample means this is our test sample. And what we need to do? We need to classify this test sample. So how my system will predict the class of this sample? Anybody? What would be the class of this test sample? Yes.
Green.
Green means non-malignant. That is the class, non-malignant. Why? What is the reason? Yes? What is the reason?
It belongs to that class.
No. How? See, whenever I am presenting a test sample, I need to have some mathematical computation to find out the class. So here we are having a simple criteria. Right? So what is our criteria? We have defined the threshold. Correct? No? If the tumor size of the new sample is less than this threshold, then we are going to declare class of that sample as non-malignant. And if the tumor size of the sample is greater than the threshold, then we are going to declare that sample as malignant. So simple it is. And this is how we are making use of this threshold. Are you getting me? Yes?
Yes, ma'am.
So this threshold is nothing but some tumor size that we have decided. Right? So if the sample is having smaller tumor size than the threshold, then it will be detected or it will be classified as non-malignant, green class. Okay? Now, similarly, and this new sample, test sample, black dot, and if I want to predict class for this particular sample, then once again we are going to apply the same criteria. And what is the criteria? We'll check what is the size of the tumor for this sample. Correct? So if size of the tumor is greater than the threshold, then obviously we will declare class of this sample as malignant, or in our case. Right?
Yes.
Fine. So, all the samples, those are towards left hand side of our threshold or decision boundary. We are designating those samples as non-malignant, and the samples, those are towards right hand side, meaning the size of the tumor is greater than the threshold, then we are going to designate that sample as the malignant sample. Okay, now let us check now one more sample. Suppose I am having this sample. Okay, this this black dot. So this is now my new test sample. So please tell me now what would be the class for this sample. Yes, we are having the threshold over here. This is my threshold. So what would be the class for this new test sample? Apply.
Malignant.
It is
It will be malignant.
okay.
Yes, ma'am.
So, as per our criteria, we are going to designate this test sample as malignant, right? Because the tumor size for this sample is greater than our threshold. Okay? But now, if we look at this particular sample, if I look at this particular sample, is, even though due to this threshold, this sample is predicted as malignant, this is more close to my non-malignant class than the malignant class. See what I am saying. If I look at close these samples, then what I can say is, or what I feel is, so my system has predicted this sample as malignant. This sample is more closer to my non-malignant class samples. Do you agree with me?
Yes, ma'am.
Yes? Right. So I feel that it would be more accurate if this would have been classified as non-malignant. Right? Because looking at this sample and the tumor size, what we feel is like this should be non-malignant instead of predicting it as malignant. Right? But as we have defined the threshold here, it is being predicted as malignant. So in fact,
Ma'am, on what basis we have defined the threshold value?
yes, right now we have decided it randomly. Okay? But now we are going to discuss the same thing, how to determine the threshold. Okay?
Okay.
So, once again, look at this screen, and what we have on the screen is our original data. Okay? So, we are having few samples, those are non-malignant, and we are having few samples, those are malignant. Okay? And what we need to do is, we need to come up with the threshold. Okay? Our data is one-dimensional data. So, every sample is described by making use of tumor size. Okay, and earlier we have selected one threshold, and accordingly we have seen few test cases wherein we try to classify our test samples. Now let us see what we can do to come up with a better estimate. Okay, see here, this is the sample, green sample, which is at the boundary. Okay, and similarly, this is a red sample or the malignant sample. So these two samples are at the edges of two clusters. So I am saying that this is one cluster wherein I am having group of non-malignant data samples, and this is another cluster where I am having the malignant samples. Right? So what I'm going to do next is, I'm going to consider these two samples. Those are at the edges of two clusters. Right? Or in other words, I may say that these two are the nearest observations belonging to two different classes. I'll repeat, these two are the nearest observations or the nearest examples belonging to two different classes. Do you agree with me? Yes? Yes?
Yes, ma'am.
So, once we have picked up these two samples, what next we are going to do is, we are going to come up with a threshold. Right? So once again, this purple block is our decision boundary or the threshold. So how we have come up with this threshold now? This is actually the midpoint of these most nearest samples, those belong to two different classes. So whichever are these two samples at the edges of the two clusters, we have picked up these two samples and we have found out the midpoint of the distance between them. Right? And we have selected this as our decision boundary, or this is our new threshold now. Right? So if I am having now this new test sample, the same test sample that we have seen earlier, which was classified as malignant in the earlier situation, whenever we had the threshold somewhere here. Okay, now we have changed the threshold with some criteria, and now the same sample is being classified as non-malignant. Why? Because now this is my new threshold and this test sample towards left hand side of my decision boundary, and that is why we are now predicting this sample as non-malignant. And now I feel that this is more accurate prediction. Do you agree with me? Yes?
Yes, ma'am.
May I proceed?
Yes, ma'am.
Fine. Now discuss one concept here. So what we did, we have picked up two samples at the edges, right? And what we did, we found out the midpoint and we denoted that midpoint as our threshold or decision boundary in this situation. So obviously the distance from this green point to this decision boundary and the distance from this red sample to the decision boundary is same. So these two distances are same, and these distances are known as actually the margins. So the shortest distance between the samples or observations, right, and this threshold. So these shortest distances between the samples or the observations is known as the margin. We say that the distance between the observations and the threshold are the same. Both are actually reflecting the margin. So this is our margin, right? And these margins from the threshold and the sample belonging to either of the classes is same. So when a threshold is a halfway between the two observations, the margin is as possible. Margin, this entire. So this is the largest. Okay, I'll repeat. When a threshold halfway between two observations, the margin is as large as possible. And when we use the threshold that gives us the largest margin to make the classifications, we say that we are using a maximum classifier. I'll repeat. When we use the threshold that gives us the largest margin, we are using a maximum margin classifier, and support vector machine is actually a classifier of this kind, maximum margin classifier. Are you getting me? Yes.
Yes, ma'am.
So I hope you must have understood this
Yes.
concept of maximum margin classifier. To come up with this threshold, between the sample two different classes. That is the essence. Right? And this is one simple example in one dimension so that we can understand the concept. Now, in the next class, we are going to extend the same concept, right? For more than one dimensions, and also we are going to talk more upon the technical details of this maximum margin classifier. Right? So I hope you must have understood this concept. Please remember, support vector machines are really very popular because they are being used to classify the data even though it is linear or non-linear. Whether the data is linearly separable or whether the data is linearly non-separable, in both the situations our SVM will provide us the solution, and that is why this is one of the most popular algorithms that is being used for classification, right? So in coming sessions we are going to discuss at depth about this support vector machines, right, and various properties of support vector machines. So let's stop today. I hope you must have understood all those concepts. If you have any doubts, please let me know. In
No, ma'am.
okay, so let's conclude. Thank you.